Okay, better. I'll try not to touch it. Do I need to use this one? Is it better this way? Okay, I'm going to use this one. I think as earlier talk mentioned, it's clear that today computing is bottlenecked by data. And data is really key for many applications. It's not just machine learning. There are many other applications that are quite interesting. Genomics is an area that we work in. And these applications are becoming more data intensive. And we want to do more sophisticated things on the data. I think data intensity is one of the reasons people are buying tape. I'm not sure about the latencies, though. I'd be happy to have a discussion on that. Clearly, machine learning is in everybody's minds. Compute and memory requirements here are growing. That's why people are investigating different types of approaches to chips. But I believe genomics is going to be even bigger into the future because it encompasses machine learning within itself. So this is a domain where lots of different types of workloads actually combine together to achieve some big goals in medicine, public health, etc. So in my opinion, we also have a responsibility for the future as engineers, as people who develop infrastructure that's going to be used by everyone all over the world and the universe. Do we want a future that looks like this? Or do we want 1930s Pittsburgh, where I used to teach? I'd prefer the first one. But as human beings, we're greedy. We want high performance, energy efficiency, and sustainability all at the same time. And I believe we're at a point today that we cannot tolerate giving up any of these. Then let's take a look at what we do in our computers today. Basically, today, we're wasting a lot of energy because we're moving data across all of our systems. We're also wasting a lot of performance, but we don't often think about it. This is something that's a hidden cost. I'm sorry, what's going on here is a bit weird, but hopefully it will stop. I'm going to talk about robustness also. Robustness is actually one of our biggest problems before we go into in-memory computation, but we need to make in-memory computation robust as well. Okay, so we don't actually see the performance loss because this is kind of a given, right? We actually try to cover up for this performance loss by designing very complicated systems, which make performance even harder to get in our systems. Okay, I'm going to keep fighting against this computer for a while. Let's see. So, and the fundamental problem is that processing of data is performed far away from the data. Today's systems are very processor-centric. All data is really processed in the processor at great system cost. I'm going to give you some data to motivate this very quickly. But I'll show you this picture that I like. This is a picture of a modern chip, kind of. I actually drew this picture in 2008 when I wrote my first proposal to the National Science Foundation in the United States when I was at Carnegie Mellon. The picture is somewhat similar today, but you have a lot of accelerators. Basically, most of the system is really dedicated to storing and moving data. Even if you look at a processor chip, we call this a processor chip, but more than 90% of this chip is really dedicated to caches, memories, interconnects, communication, and storage. And if you put this picture in front of a 10-year-old and ask the question, I should not have a problem with memory, right? And they would tell you, of course, you should not have a problem with memory. But unfortunately, our systems are still bottlenecked by memory. And if you don't like my picture, this is a real picture from AMD. That green box is caches, not all caches. L1 caches are not included. Okay, we're fighting still. I hope this keeps you engaged. And then we're adding more and more caches with 3D technology. This is IBM, caches, memory, interconnect. And this is another system where we have chiplets, beautiful technology with a lot of SRAM. And then there's DRAM, and then there's a darkness that nobody thinks about. We like thinking about, of course, right? So basically, I think you get my point. Data really is overwhelming our systems today. It overwhelms our memory capability, communication capability, and in the end, computation capability. And we've been building, we're building the fastest possible systems that we've ever built. Unfortunately, we're starving them. And also, data greatly impacts robustness, energy, performance, and cost. And I will keep doing this until, I think it's the screen. Maybe I have a good idea of this. Let's try. No, that's not what I want. Okay. I think this dual screen setup is messing up my computer. But okay, but we knew that memory is a problem, actually. This is data from like 30 years ago. This is alpha processors. The Excite said that basically when they built the fastest possible alpha processor at the time, they said this is a beautiful processor. We built it to finish 4 alpha instructions every clock cycle, which was a fast clock cycle at the time. Unfortunately, it's finishing 1 instruction every 4.7 clock cycle on this important data-intensive workload, on a database workload. And, okay. Is there a way to solve this problem? What do you think? Like, can I give my slides to you, or This was not a problem earlier, but okay, how do we? I think this dual screen setup is really.
You don't have any timer, right?
I don't have any timer. No, I don't have anything sophisticated, really.
So just to see, you go just like not in presentation mode, maybe.
Okay, but that's not very good, I think.
Yeah.
I never had this problem in this place before. Display. I'm sorry. Let's see. Arrange. Oh, I cannot even arrange this place. I don't know why. That's really weird. Okay, Z-pad, that doesn't work. Okay, let's see how it goes. Okay, this is data from my own PhD thesis. Okay, basically, Dick Sykes finishes the article. This is a one-page article I would recommend everyone to read, saying that I expect that over the coming decade, oh no. Memory system design will be the only important design issue for microprocessors. This is data from my own PhD thesis where we showed with Intel exactly the same thing. More than 50% of the time, the processor is waiting for data to come back. And if you're interested, you can take a look. This data from Google. According to them, all of their data center workloads, most of the time, the processor is waiting for our data to come back. Okay. Yes, I think that might be the best solution, you know.
Find out.
It's a complicated setup here. Okay. Yeah, I'll put this here, but not good. This is a good time for a break, probably. Okay. I don't see the. Oh, okay. Wait. No, I don't see this this thing. Yeah, I couldn't copy it though. That's the problem. Here, remove this. Maybe this is causing some problem.
Can you see the USB? It's not plugged. Okay.
Okay. Okay, now it's here. Okay.
Unplug.
Unplug. There you go. Is it okay? Yeah. Try one more time here. Maybe with this one it's better. I use another. Okay. I think it's okay. I use another connector. So if this doesn't work, then we'll switch to that one. It's good to have a backup though. Yeah, I think there are multiple issues. Sorry. Okay. Should I continue? I think I found some other solution. Okay. Okay. Should we continue? Okay. I think this points to the importance of robustness, frankly, in our computing. I'll get to that. One of the reasons for, I think, moving to more closer to data computing is really robustness. We do a lot of work in that area too. Okay, but this is Google's work that showed that according to them, all of their data center workloads, again, bottlenecked by memory. Most of the time, the processor is waiting for data. Okay, so I think I've given you these key system trends, especially for performance. Let's take a look at energy. Energy is much worse. This is a slide that's old. We actually have new numbers, but we couldn't put them in a paper yet. But this is from Bill Daly. It basically shows that a sophisticated arithmetic operation floating point is much cheaper than a DRAM access. And there's an 800x difference in this case. Yes, you can optimize it, but basically a memory access is more than 100x more costly in terms of energy compared to a sophisticated arithmetic operation. People are trying to reduce the arithmetic operation sophistication, right, complexity today by going into smaller data types and also integer as much as possible, avoid floating point. And if you do that, if you go to shorter, like 32-bit add, then the difference amplifies to 6400x. Now, if you actually have 1-bit add, 2-bit add, 4-bit add, that difference amplifies more. And we're not even talking about storage, this main memory. Talk about storage, then you go another order of magnitude. So these numbers, in my opinion, are crazy. We're actually moving data, expending 10,000x or more energy to get the data to the processor from the storage system. I'm not even talking about the network or the sensors, etc. If you go over there, it's actually much worse. And we built this hierarchy that's really wasting so much energy and so much infrastructure. And to overcome this, we're actually adding a lot more complexity to our systems. So think about sustainability and energy. This is hidden costs. We don't think about it overall. And when you actually write about them, people say, oh, this is how things are designed. So whenever you make your in-memory computing system, you should make sure it works with everything else we designed. But maybe we should not be designing everything else the way we're designing them today. Okay, so let me give you some more data. Basically, this is what we did with Google also over the years. And we found out that on average, mobile applications, more than 60% of the energy is spent on data movement. More recently, we repeated the study using edge TPUs. This is edge machine learning accelerators. And we found out that in especially large models that are executed on these Google edge TPUs, more than 90% of the total system energy is spent on memory. And this is just to give you an idea. I'm not going to talk about this paper in detail, but if you look at the large models at the time, transducers, LSTMs, transformers are actually similar. Most of the energy is really spent on, okay, I have to use this one, I think. Most of the energy is really spent on DRAM and interconnect. Processor is actually minimal over here. And if you go to a more memory-centric, near-memory computing approach, you can reduce that energy by about 5x or so. Okay, basically, we do not want to move data. We need a paradigm shift to minimize data movement as much as possible. And I build computation in other parts of the system, not just the processor or accelerators. And we want to make computing architectures more data-centric. And there are many places where we can do computation. Why are we restricting ourselves to a very small fraction of this SRAM-dominated chip? Now, this is, I'll give you the big picture. I'm going to talk about some ideas in DRAM, especially today, but we do work on DRAM, flash memory, and other types of memory technologies. We cover almost all aspects of it, and I think it's a fascinating area. We'd like to enable something like this. We'd like to tell memory, can you execute this function for me? And the memory says, yes, here are the results. That sounds good. This is still an accelerator model. There are much more disruptive models that we're working on. I'd be happy to talk about that. There are many questions, even within this accelerator model. How do we design the memory and controllers, processor and communication units, software and hardware interfaces to enable this, system software compilers and languages to take advantage of it, and also algorithms to actually really hit the hardware underneath. This was mentioned by the previous talk, but if you want to make it even general purpose, not just for machine learning, there's a lot of steps that we need to take. This is really across the stack problem. And I also like thinking about theoretical foundations of computing. If you think about the theory of computation, it's very, very processor-centric. You count operations. But everything I showed you earlier says that maybe operations are not that important from the grand scheme of things today. Maybe we should really develop a theory of computation that's much more data-centric, that takes into account data movement and energy, as opposed to the number of operations that an algorithm does. It's good to think about. I should also say that this is not a new idea. We're not the first, and a lot of people who are working on it are not the first. This idea was developed in the 1960s, at least, maybe earlier. And these are some beautiful papers that are written by folks like Kautz and Harold Stone. These folks envision near memory computation, not using memory computation like what I will describe, especially today, because we won't have time for near memory computation. So what is different today? This is an idea that's more than 60, 70 years old, in my opinion. I think today we have nowhere to escape. Essentially, we have come to the end of technology scaling the way we have done. And as a result, we are having huge problems at the lower layers of the stack, technology layers, like robustness issues that I'll also come into. Memory technology scaling is not going well, and scaling issues demand intelligence in memory, plus new technology is coming also, in my opinion. I'm going to talk about that briefly. I've already talked about the huge demand from application systems. We're kind of squeezed in the middle. At the top of the level of the computing stack, users and the applications are squeezing us to do something different. At the bottom of the stack, even memories that we have relied on a lot are squeezing us to do something different. So we're squeezed in the middle. And also there's new technology coming like 3D stacking that will enable new things, in my opinion. That's I kind of put this in the memory technology part. So I'm going to mention RowHammer very briefly because it's a technology scaling problem that actually demands intelligence from memory. Today in DRAM chips, you can predictably induce bit flips. We do a lot of work in this area. I'm not going to talk about this in detail. This should not be happening. You should not get bit flips in DRAM chips. And actually, this what I found out was I had a robustness problem in this thing earlier. This thing was not working. So I replaced it with a much better communication device, and it works right now, right? So that's what we need to do also, I think, in memories going forward. So we've written a lot of papers on RowHammer, and we've always argued that to overcome technology scaling issues where the underlying technology doesn't work too well, you have some robustness problem, you have some energy problem, you can usually overcome this by taking a system-level approach. You can still make use of the underlying technology by designing intelligent controllers that overcome the disadvantages. And we knew that from flash. We did a lot of work on flash memory, and a lot of people here, I think, worked on flash memory SSDs. The reason that flash memory technology works is the controller. It's not the flash cells themselves, because they're terrible in general. But the controller makes them work by programming them and actually making them robust. We need that in main memory also. We never needed that in the past. And, okay, I think. And the good news is, finally, industry is recognizing the problem. This is a paper from ISSCC, SK Hynix. This is the first paper from a major DRAM vendor that admits the problem. And that basically says, we're trying to solve the problem by adding essentially what we just suggested, adding intelligent controllers inside the DRAM chip. Now, I'm not sure if this is the best approach. We have papers talking about it, et cetera. But basically, they're adding counters with every row. And internally, the DRAM chip is manipulating those counters and taking some action if the counters are larger than some threshold, so that hopefully you don't get bit flips. But this is computation inside the DRAM chip that's already going to happen. And this was adopted by JEDEC very recently in April 2024 for row activation counter solution. So this is what I mean by technology requiring more intelligence and computation capability. And people are pushing it inside the DRAM chip today. Okay, I'm not going to bore you with more RowHammer, but hopefully robustness is important. I'll point you to some PhD theses that my students have written. But there's more coming. This is not just about RowHammer. It's really about technology scaling. And we have more recently shown that even if you're not able to hammer a row many times, activate a row many times, you can actually open a row, activate a row, and keep it open for some time. And the disturbance that you cause because of the row is open, activated for a long time, causes bit flips in nearby rows. In extreme cases, even if you activate a row once, you get a bit flip after waiting for some time. This is fascinating to me. It's very interesting. We did a lot of testing to understand this, and this paper discusses it. Are we doomed is the question, I think. In my opinion, I think if you design good controllers, you can fix some of these issues. Okay, so at the higher level, I think processing in memory landscape today is very interesting because we have 3D stacking technologies, and also people are investigating new chips. And you can buy, for example, near memory processing chips from UpMem. And people are also been publishing, like Samsung, SK Hynix, Alibaba. They're actually changing the DRAM chip so that they can accelerate essentially multiply and accumulate operations. And there are many other startups and experimental chips. I'm not going to talk about these. This is near memory computation, which is, I think, easier to do. I'm going to talk about what's harder to do, which is using memory computation, and hopefully give you some results. Okay, and then there's interfaces, but at the system level, I think it's good to think about interfaces as well. Today, there's Compute Express Link, CXL interfaces that are going to make it easier to offload computation to the memory and storage devices going into the future. And there are papers and talks about this. We cover a lot of this in our archive paper that talks about a lot of these issues. I'd be happy to recommend this to you, but we also have processing in memory courses. We have a lot of courses and tutorials. So just to give a pitch, we have an upcoming processing in memory tutorial at Micro. We'd be happy to have participation, and this is all online. Even if you cannot go to Austin, you can actually join us online as well. Now, let me give you some results from recent as well as past studies. I believe we need to think differently from past approaches. Processing near memory is interesting. It's an interesting approach. That's, I believe, easier to happen, and it's already happening. So what is processing near memory? Essentially, you have logic and memory. You put logic closer and closer and closer and closer to memory, integrate it with memory arrays, etc. But logic and memory are designed separate. Processing using memory is fundamentally different, and it was developed more recently than 1960s, in 2010s or so. The idea is you have logic and memory. Forget about logic. Imagine logic doesn't exist. You have just memory. This memory has fundamental analog operational characteristics that you can exploit to do computation. And that's the idea over here. Can we make this work? Can we make this reliable? Can we make this general purpose? Can we actually build an infrastructure around it? In my opinion, it's very difficult to do things just using memory. In the end, we need to combine using and near memory together. Using memory is much more efficient if you can really understand where that could be useful. But I believe we need to combine these together. Okay, I'm going to skip this one because I've already explained. There's a more general processing and memory taxonomy that we're working on. What I just talked about is the nature of computation, but then there's a technology, and then there's a location from the system perspective. And a processing and memory type is really a tuple of these things. In the end, you can enable all types of computation across all of these Cartesian products of this, which is very interesting to think about. Today, we actually have none of these almost except processor, right? Okay. So we're going to keep the mindset as memory as an accelerator. So let me give you some examples from a particular type of thing that we've been working on for a long time, processing using DRAM in main memory. And we also have a talk at IEDM coming up because they were quite interested in, I think, this topic. So we're going to talk about this in more detail. Just to give you a key idea, after the slide, you can perhaps go to sleep. I'm going to give you some examples, but this slide basically summarizes what we can support today. We can do bulk bitwise operations and or not majority, even in real DRAM chips that are not designed for this purpose. By violating the timing parameters, we showed that you can actually do these reasonably reliably in real DRAM chips. This is fascinating to me. You can do bulk bitwise copy and initialization, which is, I think, a no-brainer today. True random number generation, physical unclonable functions. And also, if you want more complex computation, you can treat memory as a lookup table, and you can do lookup table-based computation. At low cost, using analog computation capability, essentially activating multiple rows either concurrently or sequentially in DRAM. Yeah, and we show that you can do it in commodity off-the-shelf DRAM chips. And you get a lot of performance and energy improvements. This is just an example. I'm going to give you some more examples. So let's start simple. Let's talk about data copy and initialization. We do a lot of data copy and initialization today in our systems. Like if you initialize a 30 terabyte database or 30 terabyte model, you put zeros over there, for example, right? And Google in their seminal paper showed that approximately 5% of their data center cycles is spent on copy, on just these two functions called memo and copy. So how do we do copy today? If you want to copy block data from this place to this place in memory, you essentially need to go through the processor. Okay, clearly this is a lot of disadvantages that we just talked about earlier. I'm not going to bother going through them again. But I think we should really take a blank slate approach to our systems. Maybe showing this picture to a 10-year-old helps. Show this picture to a 10-year-old and say, I'm doing this today. What do you think I should do? Maybe they'll be a lot more honest with us and they will say, why don't you just do this thing? And I believe this is how we should think going into the future. And this we can do today. I'll show you a lot of results related to this later on. But basically, you don't go through the processor at all. You do everything inside memory. As a result, you get significant reduction in latency and energy. Now, of course, you need to design the system to take advantage of it. And that will come over time, assuming we can build these things. And I'm going to show you that we can actually build these things relatively easy. So what makes this work in DRAM? Other technologies are similar. We've shown that you can do it in Flash also. But basically, if the source and destination rows are in the same subarray in DRAM, they are connected to each other through the sense amplification circuitry. You first activate the source row, which brings the data into the sense amplifiers row buffer, and then activate the destination row in sequence after very little timing margin, which brings the data from the sense amplifiers to the destination row. So basically, it's really analog charge sharing, right, with sense amplification in between. And we showed initially that you can do this with negligible hardware cost if you want to do it reliably. Again, I will skip some of these slides since we kind of had this mishap with the robustness, but also you can study these slides. But essentially what we're doing is we're exploiting the charge sharing operation through one cell to the sense amplifier, and then through the sense amplifier to the destination cell. So benefits are significant at the system level, both in terms of energy and latency. And we have application level results in the paper that I'm skipping over here. So the fascinating thing is, after we published this, other folks using our infrastructure showed that by violating the timing parameters in real DRAM chips, you can do this operation. And then we built on their work to actually design an FPGA-based infrastructure. You can download this infrastructure, you can test it on your own, where we can offload page copies to a RISC-V processor on the FPGA. And the RISC-V processor sends that page copy operation to the memory controller, such that the memory controller does the copy and returns the result to the program. So you can actually have an end-to-end program that can do this on an FPGA-based system today without changing the DRAM chips. This is existing DRAM chips by violating timing parameters. And we show significant performance improvements because the processor is actually not very good over here. But the real performance improvements, if you have a very good processor, should be lower than this, but still significant. Okay, we'd be happy to help with this if people are interested. So you can ask a lot of questions. Okay, this is restricted to what's within subarrays. You need to do the data mapping, etc. Yes, absolutely. I agree with all of that. You need to think about the system, given that you have this fundamental primitive of copy initialization right now. And there are a lot of work that talks about this that I'm not going to cover. What I'm going to cover is something else, which is computation now. You say data copy initialization. I don't care about it. I think people should care about it. But what about computation? Now, let's talk about computation. I've already shown you the slide. And I believe in emerging memory technologies also, but DRAM is still fascinating because I think the future of memory is DRAM given the next 5 years or 10 years. Still, at least the low latency memory is still DRAM. Okay, so how do we do computation in DRAM? This is one example. If you concurrently activate these 3 cells in DRAM, I'm showing you only 3 cells, but imagine an 8 kilobyte row. You could do this in 8 kilobyte rows, plus you can have thousands of subarrays. You could do it in millions of bits, basically. If you concurrently activate ABC, theoretically, based on charge sharing principles, if at least 2 of these cells are charged, you would get the charge state at the end in the bit line. If at least 2 of these cells are discharged, you would get the discharge state. Now, that's a bitwise majority function. That's beautiful. You could try writing all of your applications using this block bitwise majority function. Difficult. You could take out C, set C to 1. You get OR and AND, which is also good. Now, what's missing is NOT, but NOT is already there, actually. If you actually activate one row, you get the complement of the value over here. You just need to supply it somewhere so that we can reuse it. So we actually have a functionally complete circuitry, and we discussed this. So what is it good for? It could be good for everything because you have AND and NOT, or majority and NOT, which is functionally complete. If you rethink your algorithm and be creative about it, you should be able to rewrite every program to take advantage of it. But there are some programs or some algorithms that are much more, let's say, amenable to this because they work on bit vectors and bitmaps. And we've actually ported databases that work with large bitmaps to our simulator, and we see significant performance improvements and energy reductions. So this is old work. But I'm going to cover some recent work also. I think this is fascinating. And then we made it more programmable. Programmability is really important. I'm going to mention that at the very end of the talk. Programmability is really important. And in this work, we basically provided a framework where a user can express any operation. I think I've lost it. Okay, a user can express any operation over here. And as long as you can express it using a hardware circuit like this, we can take it and using majority inverter graphs, we can optimize it. We can generate a microprogram that essentially has a sequence of DRAM commands to implement that operation. And then we store that microprogram. When the user actually uses that instruction through a compilation process inside a program, that instruction gets shipped to the memory controller. Memory controller executes this microprogram, and then actually it does everything in memory for that instruction. Now, there's a lot of details over here, which I'm kind of not covering, but you see significant performance and energy improvements compared to state-of-the-art CPUs and GPUs, especially energy efficiency improvements are significant on real applications. Okay. So we need to make this more flexible, especially compilation is a difficult target. If you're working with 8 kilobyte rows, it's very hard to get a compiler to compile or even discover parallelism across 8 kilobyte rows, unless your application is really written using these bit vector paradigm or set paradigm, which we also explored. So what we tried to do in more recent work is to try to reduce the granularity. So one of the issues we have with memory systems today is the granularity of access. You actually access a lot of data, and then you bring in very little data. This wastes a lot of energy internally and even at the interface level. So we tried to reduce it. In this work, we basically argue for, I'm going to skip that one, argue for enabling fine-grained access in DRAM so that we can do this operation at a map level or a portion of a subarray level. essentially, instead of activating the entire row, can we activate a smaller portion over here? That's the idea. That's not a new idea. People have looked at fine-grained DRAM in many incarnations, etc. But we use it for processing in memory. And we actually have a version of that coming up in the High-Peak conference. That is a low-cost version of having DRAM so that you can access individual mats as opposed to activating the entire subarray, entire row. And if you do this, what you can do is you can improve the utilization of DRAM. You can actually do something in these mats and something else in these mats, some other operation in these mats. That's why it's called multiple instruction, multiple data. You can, for reduction operations, you need to do processing near memory that I'm not going to talk about over here. So I think in this work, we combine processing using memory as well as near memory. And also we can ease programmability by actually having a compilation target that's on par with existing ICs, like AVX has a vector width or SIMD width of 512. Now we can actually target that compiler to a in-DRAM computing engine. And that's what we did in this work. We open source this compiler. If people are interested in using it, we have a compilation flow that goes into this using method. Okay, and then if you actually do all of that, you get significant energy efficiency and performance improvements compared to existing CPUs, GPUs, and also SIMD-DRAM work that we have developed previously a few years ago. Okay, I can bore you with a lot of results, but you can find more information. Okay, in the remaining part, I will tell you that, so you can tell me everything I said so far. What are you smoking? I kind of agree. Sometimes when you actually talk with industry, you get that kind of thing. In a sense, it's true because this is analog computation. It's not perfectly reliable, right? And this is DRAM also. It's very brittle in a sense, right? It's not flash. Flash is not brittle. DRAM is very brittle. So another effort that we have in my group is really testing these DRAM chips to see what they're really capable of. And we use the infrastructures that we've been building for more than a decade to test DRAM. These are actually open source infrastructures. Anybody can use it, and we'd be happy to help with. We more recently have the DRAM vendor where you can actually test DDR4 chips as well as HBM2 chips. We have papers talking about it. And again, a lot of people from industry and academia ask us for help, and we are open to helping anybody who's interested in testing memory in general. But we found out, again, in papers published earlier this year, that you can actually do a lot of things that we have envisioned in real DRAM chips in slightly different ways. Basically, the idea, I'm going to cover the key ideas very quickly. Basically, you can simultaneously activate up to 48 rows, not just 3 rows, but up to 48 rows in neighboring subarrays and also in the same subarray. You can perform the NOT operation with up to 32 input operands. So 32 input NOT, imagine that. You can also perform 16 input and NAND and OR operations. Now, let me give you the key ideas. Basically, by violating the timing parameters, you don't change the DRAM chip, you don't change the DRAM interface, you change the memory controller. And we have an FPGA-based memory controller where we can change. By violating the timing parameters, meaning activating 2 rows in quick succession, you can activate multiple rows in neighboring subarrays. So instead of obeying the timing parameters today, let's violate the timing parameters. I'm not suggesting that you do it for real purposes. The goal is to demonstrate what DRAM chips are truly capable of today, even without changing them at all. Now, if you do that, you can activate many rows, 48 rows. You can actually do more, but we report 48 in the papers. So how do you get NOT? NOT is possible if you activate the source row in the top subarray. I'm showing you one cell. Essentially wait for some time so that the data is actually over here in the sense amplifier. And then with quick succession, before this settles actually completely, you activate the destination row. That way you get the complement of A in the other subarray, which is great. Now you can actually take advantage of it through compilation, etc., which we're working on. Now, what's even more fascinating is NAND, NOR, AND, and OR. Actually, I believe you can implement any function in DRAM. You just need to be very careful about it. So we're looking at 2 subarrays. I'm showing you only 2, but you can actually do it up to many input operands. This is the reference subarray. This is the compute subarray, as we will see. If you look at the sense amplifier, if you concurrently activate all of those, what sense amplifier does in an ideal circuit is it compares the average voltage of A and B to the average voltage of X and Y. And the result is really that comparison result, right? That sounds good. Now let's see what we can do with this one. I'm going to show you AND and NAND, but you can do OR and NOR as well. In the reference subarray, assume that you store VDD and VDD over 2, and then we have a way of actually carefully storing VDD over 2 in DRAM based on some previous work. If you're interested in that, I'd be happy to talk about it. So you can actually manipulate some charge in DRAM similarly to the way you manipulate charge in flash, but with less control. And the compute subarray, we're going to do computation on it. Okay, we're going to violate the timing parameters. We're going to activate all of these by violating the timing parameters. This is the result from IEDM chips. So what the sense amplifier will do is compare the average of 3 VDD over 4, because we've already stored it, to average of x and y, and x and y are the input variables to the function. So if x and y are 0, clearly the comparison of 3 VDD over 4 to 0 is larger. So sense amplifier will push the upper bit line to VDD, lower bit line to ground, and you get this 0 in the compute subarray and 1 in the reference subarray. If it's 0 and 1, similarly, the average of that is smaller than 3 VDD over 4, you get the same result. Okay, if 1 and 0, again, you get the same result. What's interesting is 1 and 1, meaning the voltage over here is greater than the voltage over here. So in the end, you get 1 in the compute subarray and 0 in the reference subarray. Now, if you look at the function that you get in the compute subarray, it's an AND. If you look at the function that you get in the reference subarray, it is NAND. This is theory. And hopefully you're comfortable with the circuit theory, because it is what should happen, assuming you don't have variation, etc. Now, you can do this in real DRAM chips. Let's take a look at the results from real DRAM chips. And these are the number of input operands you have to AND, NAND, OR, and NOR over here. And this is a success rate, a reliability, robustness metric. And you can see that the robustness is actually larger than 94%. Now you can say, yes, 94%, but I want 100%. I want 100% too. I agree. But this is DRAM chip that's not designed for this purpose. Nobody advertised a DRAM chip to be doing this. This is uncovered functionality in existing DRAM chips. Okay. And there's impact of data pattern, temperature, etc. All of these need to be studied. Right now, we're studying actually how to do this more reliably by changing some things in the DRAM chip. I'd be happy to talk to people about that. Now, there's something that you can do a lot more reliably in DRAM chips. That's data copy and initialization. And that's why this is a no-brainer, in my opinion. So we have found out in a concurrent work that instead of just doing copying from one row to another, you can do copying from one row to many others. Again, using the same principles. You activate the source row, and then you activate many rows in the same subarray, which means that the data is copied from the source row through the sense amplifier to many rows. And we found out that you can do this up to 31 other rows. And this is a success rate, more than 99.98%. And this is not that much dependent on temperature. It's a data pattern. We study that. I think this is fascinating. You can say, I want 100%. I agree. I want 100% too. And that's the goal. How do we get to 100% with this? But I think these results are fascinating, promising, because again, the DRAM chip is not designed for this purpose. When we talk to DRAM manufacturers, they also say this is fascinating. So we have some validation on this one. Okay. So there's a lot that needs to be studied. This is all open source. If people want to build on it, we'd be happy to help. These are based on our infrastructure, FPGA based, but everything is open source, artifact evaluated, reproduced by independent people, so you can find out more information. So what else can we do using DRAM? In the remaining time, I'll very quickly go over that. We can do essentially true random number generation using our infrastructures. We showed that by violating the timing parameter in existing DRAM chips, some cells fail randomly. And these cells can be used as random number generator cells. You need to profile those cells, but you can do this reliably at high throughput and low energy. This is old work 5 years ago, but we actually showed that you could do it. So this is important for building a security infrastructure on the memory side. And I believe any kind of infrastructure should be pushed to the memory side. You can also do other stuff, and we have more works in this area. You can also do physical unclonable functions. That's important for remote attestation, etc., and security, and I'd be happy to talk about that separately. If you want to do more complex operations, this is something that's interesting, and I think I encourage people to think, how can you do more complex operations? DRAM is not good for matrix vector multiplication. That's very tough. You can express convolution, matrix vector multiplication as a circuit, and then implement it on the serial substrate like we've done in the SIMDRAM, MinDRAM works. It's not as efficient as it could be, but it's better than actually what you could do with the existing systems. But lookup tables actually offer a good opportunity, and lookup tables are very interesting to study, I think. What about other types of memories? Other folks earlier, and maybe later, will talk about other type of memories, but we also do a lot of work in flash. And we've shown that you can essentially do everything that I said in NAND flash chips as well. Basically, you can do a 32 input or AND. The reason is, again, whenever you activate multiple rows, for the result to have a flowing current, everything needs to be connected in the bit line. And if you have one open circuit, meaning a cell is 0, you get a 0 at the end. Again, you can have an AND function very easily in flash memory, and we showed in this work that you can have this very reliably. You can also have an OR function. And flash is nice in terms of not, because existing flash chips already give you the inverse of the data that you're looking for. It's called inverse read in flash. So we overcome one very difficult problem in flash. Now, the flash is very interesting because you can do a lot of things reliably. In this works, we show that by manipulating the voltages, meaning incremental step pulse programming, you can do everything with 100% reliability. You need to trade off capacity. We are able to do this in SLC, single level cell flash. With multi-level cell flash, I believe this is harder, but that's part of the research going forward. Okay, so yeah, these are the results. Basically, no changes against flash chips. With small increase in sensing latency, you can have many operands. And the programming approach that we have significantly improves reliability. We essentially observe no bit error rate. If in the earlier terminology, 100% success rate, which we cannot get with DRAM today. Okay, and the results in terms of system is actually quite interesting. You can get significant speedups. Okay, if people are interested, we'd be happy to talk about it. Now, I'm almost at the end. I'm going to talk about processing near memory, but I'm not going to talk about processing near memory. This is very interesting, especially because some technologies like this, 3D stacking, we can put anything into this logic layer as long as we satisfy the thermal limitations and reliability and testing, of course. But here, we can actually do a whole lot more. This, combined with processing inside the DRAM layers or any kind of memory layers, is going to be a lot more powerful going forward. We have some works in this area that I'm not going to talk about. Adoption, I should talk about very quickly. There are a lot of issues over here. You can design any hardware, and that hardware can stay useless forever. The key is really how to make it work. And we've been working on adoption. We have a lot of works on programming, like compilation. Going forward, I think we'll have more and more works in this area. But we really need to revisit a lot of things. The toughest thing is, in my opinion, are actually these words over here, virtual memory, which has to be revisited for everything that we do in our current systems. And also, there's another tough thing over here, coherence, which also needs to be revisited, I think. Okay, but I believe we can actually change things by having a much more memory-centric mindset, but we can also get there step by step. So the good news is we can actually explore a lot of things. We explored a lot of things with the UpMem chip because this is commercially available, and we work with the UpMem company to understand the limitations. There are a lot of limitations, but even with those limitations, you can actually get a lot of benefits with these UpMem chips where you actually have general purpose, heavy general purpose processing near each DRAM bank. For example, in bioinformatics workloads, this actually shines quite a bit. Okay, let me conclude. I think hopefully it's clear that we want fundamentally energy efficient computers. They need to be data centric. We want fundamentally high performance computers. They need to be data centric. In my opinion, fundamentally secure and robust computers are also need to be data centric, but talk to me about that. We need to minimize data movement. And I think we need to start designing principled system architectures. We need to start with a blank slate and redesign the architecture. That needs to be balanced, high performance, energy efficient. This can lead to orders of magnitude improvements. I've given you some examples of this. This can lead to new applications and computing platforms. I believe this can lead to a better understanding of nature also. I'll show this with a picture very quickly, but of course, this remains to be seen. And who knows what else? I think the future is really bright, but we really are working against the current here. Everything we do is processor-centric. We really need to change that, eat away from that processor centricity. And it's really great that, like last time I was here, I didn't have that picture. All of those near memory computing chips from major companies, also startups like UpMem. Now we have that picture over here. So 5 years later, we're progressing in a good direction, in my opinion. So, but we should really think about overarching principles for computing because the way we're designing our systems is not sustainable today. And we're really destroying the world, in my opinion, especially with this greed for ML models that are being designed and that are really destroying the nature and also water sources, etc., which I'd be happy to talk about. We should really think about how to really design these things such that we can do things more efficiently. Okay, I think I'll refer you to some papers, but a lot of things we open source. We'd be happy to help with infrastructure if people are interested in getting into this. I should acknowledge people who've done this work, essentially my group and collaborators. You can find more information about them in our newsletters, and this is the latest one. Okay, this is our open source page if people are interested. Okay, with that, I'd be happy to take questions. Sorry for the robustness mishap. I'll go back to robustness. Before we do anything else, we should have robust systems.
Thank you very much for the interesting talk. Time for a couple of questions.
I think digesting the talk shows are going to pull the chips. Okay, that's to think about. But I have another question. You were showing in memory and your memory computing, in storage and your storage computing. Do you think that we need a kind of a hierarchy of computing beside the hierarchy of memory, or one of the two DRAM or storage computing has to prevail in some way?
Yeah. So, I mean, that's a good question. Basically, I didn't talk about storage as much, but we have a lot of work on in-storage computing, especially for very large data sets like in metagenomics. You have hundreds of terabytes that you need to go through. So storage is important. Memory is also important. I think we really need to do computation everywhere in the end. Over time, in my opinion, hierarchies may need to change. Right now, we have a lot of inefficiency in the system because we are not able to do computation in other places than a very specific part. Over time, I think we need to rethink the hierarchy as well, but maybe we're not at that point yet. Sure.
Yeah, I have two questions. So the first one would be, you mentioned, I don't know if I got it right, that if you address the same row repeatedly, you get write arrows or bit flips.
Basically, if you activate the same row repeatedly, you get bit flips. Yes, these are readers.
So that's naturally not occurring because you could write a software crashing computers with that.
Yes.
Is that something DRAM manufacturers were missing to validate in their qualification?
I cannot speak about DRAM manufacturers, but the overall answer is yes. And people have shown that, yes, you could crash the computer. This was also seen in the field where a program produces incorrect results. And also people have, after we published our work, produced security attacks. Using these bit flips, you can actually take over a computer.
Okay, I was thinking.
Yes, you can do all of those things.
Okay, so my second question would be, imagine you can get a ferroelectric RAM at the cost of DRAM, same density.
Yeah.
Would any of your concepts benefit from the non-volatility, or is your utilization rate so high that it doesn't matter?
Meaning any of the concepts, meaning like the read disturbance errors, or more
No, I mean,
like in memory computing?
Would you think that, I don't know exactly what you're aiming for, but is your utilization rate so high that non-volatility doesn't play a role?
I see. Okay.
Or would you still think there would be some power consumption
No, absolutely.
gain?
Yeah. I see your question. Basically, what is the role of non-volatility? I think if you have something non-volatile as opposed to DRAM, you could take advantage of it for sure. In fact, we have done work in that area. You could reduce the system level overheads of copying data from the storage and memory. You could directly operate on persistent data. You need to change your programming model and thinking a little bit for that. But I believe the benefits over there of non-volatility is in addition to what you could do within memory computation. Because that way you don't need to, there's another data moment that I didn't talk about, which is really persistent versus volatile data, right? That actually causes a lot of problems today.
Any other question?
If not, we can thanks to the speaker again.